Welcome to lecture series of Digital Electronics. I am Dr. G.Mamatha, working as Associate Professor in J&T College of Engineering, Ahmedabad. Today we are going to discuss about logic gates. Logic gates are the basic building blocks of a digital system. The name logic gate is derived because the output and input patterns of a gate are assigned logically. Logic gates work with the binary inputs, that means only 0 and 1. The 0 can be taken as either low or the false, 1 can be taken as high or true. Logic gates are implemented using transistors in CMOS technology in hardware and is used in computers, microprocessors, digital ICs, communication systems, control systems. You can say that in all digital electronics we use logic gates. And then wherever logic gates are there, truth table will be present. So truth table is nothing but the all possible combinations of inputs and then corresponding outputs for a logic gate. Logic gates are broadly classified into basic logic gates, universal logic gates, and other logic gates. Basic logic gates are AND gate, NOT gate, OR gate. Universal logic gates are NAND gate, NOR gate. Other logic gates are XOR gate and XNOR gate. When we talk about basic logic gates, there are AND, OR, NOT gates. NOT gate is nothing but the whatever input you give will get that complement of that input. If input is 1, output is 0, input is 0, output is 1. This bubble also represents the NOT gate or else the inverter. And if the symbol without bubble represents the buffer. Buffer is nothing but whatever input you give, the same output will get that. If input is 0, output is 0. If input is 1, output is 1. Basic logic gates are the AND or NOT. NOT we have seen, and AND gate and then OR gate are the two more gates. So AND gate is nothing but the A and B are inputs, Y is the output, so that Y can be represented as A dot B. So dot is nothing but the AND operation. So that AND operation can be represented in a truth table that input 1 is nothing but A, input 2 is nothing but B, output is nothing but Y. So if A and B are 0 and 0, output Y is nothing but 0 dot 0. So that is nothing but 0. And the second combination 0 and 1. So 0 and 1, 0 dot 1 is nothing but 0. And 1 0, 1 dot 0 is nothing but 0. 1 1 are the inputs. So the AND operation of 1 dot 1 is the 1. So with that we can say that any one of the input is 0, the output is 0 for basic AND gate. And if you see that OR gate, two input OR gate, A and B are the inputs, Y is the output. So A, B and then Y. If you see that operation, Y can be represented as A plus B. Plus is nothing but the OR operation. So that OR operation is 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 1. In the same way, if you see that the truth table, 0, 0, output is 0, 0, 1, output is 1, 1, 0, output is 1, 1, 1, output is 1. So if any one of the input is 1, output is 1 in OR gate. And if we see that universal gates are the preferable gates in digital electronics. Those are NAND and NOR. We can also say that it's a complement of AND gate. AND gate is A, B and then Y. If you take that inverter, so this is A bar. So here you will get that A dot B like A dot B. If you see here A dot B whole bar. So NAND gate is a complement of AND gate. NOR gate is a complement of OR gate. These two gates are called as the universal gates. Why these called are the universal gates means by using universal gates we can implement any basic logic gates that we'll see in next lecture series. If you see that to table of NAND gate, A and B are the inputs, Y is the output. So A and B output is Y. So just opposite that of AND gate, if you compare like AND gate operation A, B and Y for AND gate. So here we said that 0, 0, 0, 1, 1, 0, 1, 1. If any one of the input is 0, output is 0 for AND gate. Whereas here, if any one of the input is 0, output is 1 for NAND gate. So exact complement of AND gate is a NAND gate. And in the same way, if you see that OR gate to table is A, B and Y 0, 0, 0, 1, 1, 0, 1, 1. So here this is 0, 1, 1, 1. If any one of the input is 1, output is 1 in OR gate. But here, if any one of the input is 1, output is 0. That is exactly opposite that of that OR gate. Because of that, we are representing inverted. Inverted is the bubble symbol we are using for AND gate and OR gate to represent NAND and NOR. So these are the universal gates. And there are two more special gates are there in digital electronics. Those gates are nothing but the XOR and XNOR. So XOR gate is nothing but if two inputs are there, that Y can be represented as Y is equal to A exclusive or B. This is the symbol. Exclusive or is the symbol. And then that operation is nothing but A bar B plus A B bar. A B bar. So here we can say that output is 1 when inputs are different. So output is here 1 when inputs are different. Here inputs are 0, 1, 1, 0, then only the output is 1. And when inputs are same 0, 0, 1, 1, the output is 0. And then XNOR is just opposite to that of the XOR because of this bubble. So if you see that A, B are the inputs, Y is the output. So Y equal to A exclusive or B whole bar or A XNOR B. You can represent XNOR gate either in this way or this way. And if you see that to table here, output is 1 when inputs are same. Exactly opposite that of XOR. When inputs are same, here 0, 0, output is 1. When inputs are same, 1, 1, output is 1. When inputs are different, 0 and 1 or 1, 1, comma 0, output is 0. So these two gates are used in digital electronics wherever required. These gates called as the special gates. Now we all know that NAND gates and NOR gates, so we are calling it as universal gates. So why these are called as universal gates means by using NAND gate, by using NOR gate, we can implement any logic gate. So example, if you see here, initially we are taking NAND gate for implementation of AND gate, OR gate, and then NOT gate, buffer, NOR gate, and then XOR, exclusive NOR gate. So here NAND gate the symbol is this one. So here A, B and Q. So this can be represented as A dot B whole bar, right? So if you want to get that A dot B whole bar, if you want to get that AND operation is nothing but if inputs are A and B, the AND operation Y is nothing but A dot B and operation A dot B. So to get A dot B, already here A dot B bar is there, A dot B bar. So one more NAND gate if you take that A dot B bar bar. So two bars will be cancelled and we'll get output is A dot B. So that is a AND gate operation. And if you see that OR gate is nothing but Y equal to A plus B. But we have a NAND gate. So that NAND gate is A dot B whole bar. So here, how can we get that OR gate by using NAND gate is nothing but. So initially we'll take two input NAND gate. So these two inputs will be connected to one common input. So A output is nothing but A bar. And one more NAND gate will be taken for another input. So this is B bar. And here A bar, B bar, here this can be represented as, so A bar dot B bar whole bar. So this A bar dot B bar whole bar can be write it as, so A bar bar plus B bar bar. So these two bars will get cancelled. So finally this is equal to A plus B. So that is equal to OR gate. So by using NAND gate we can construct OR gate and also XOR gate. So XOR gate is nothing but XOR gate is A exclusive OR B. So this can be A bar B plus A B bar. So in the same way here A B two input NAND gate we have taken. So here once we take that A dot B whole bar will get here. So one input of this gate is A dot B whole bar and here we'll get that A. So A dot 8 dot B whole bar and whole bar. And again here we have to take this one B A dot B whole bar. So and then whole bar. So again these two has to be again here we'll get that uh, A dot B whole bar and here B A dot B whole bar. So and again if we add these two like an AND operation if we perform like this, so again here we'll get that A dot uh, A like A B bar and then B A dot B whole bar. So if you perform like an AND operation, you will get that plus, and again these two will get cancelled. And again by using Boolean expression like A uh, A B bar plus A bar B by simplifying this. That Boolean expression how to simplify we'll discuss later. And also XNOR gate. So XNOR gate is in the same way here. A, B are the two inputs. So in this two input NAND gate we need to take. So here this is A dot B whole bar. And again here A will be taken as here A and A. So this will become A bar. And B and here B, this will become B bar. So here A bar dot B bar whole bar. So here A dot B whole bar, we take A dot B whole bar and then A bar B bar whole bar and then this. And by simplifying this, you'll get that exactly AB plus A bar B bar. That is the XNOR operation. In that way, by using NAND gate, we can implement any gate. It may be AND gate, OR gate, NOR gate, or else the NOT gate. The NOT gate is simple two input NAND gate. If you take that, will be act as a NOT gate. And if you connect one more NAND gate to this NOT gate, so that will become buffer. A bar will become A. So we can construct a buffer, we can construct XOR and also XNOR. That's why we called NAND gate is a universal gate. And in the same way, by using NOR gate, how can we construct like OR gate, NAND gate, NOR gate, AND gate, NOT gate, buffer, XOR, and then XNOR. In the same way, we know like NOR gate is nothing but exactly complement of OR operation. So that is Q is equal to A plus B whole bar. So and again if you take one more NAND gate here, so the here A two complements will get and these two will cancel and A plus B will become, so that is OR gate. And if you want AND gate, A one NAND gate will be taken, so here this will become A bar and this will become B bar, and by combining these two, A bar plus B bar and whole bar, so this will become A bar plus B bar whole bar is nothing but A bar bar B bar bar. So these two will get cancelled, finally A dot B. So this is the AND operation. So that is a AND gate. And in the same way, how to construct an AND gate using NOR gate is nothing but here A bar one NOR gate will give complement of input A bar, B bar, and this one is nothing but A bar. So here A bar, B bar, and again we are using we are giving for NOR gate. So here this one is nothing but A bar plus B bar whole bar, and again one more gate will take like, so here will get this AB, and one more NOR gate will give the complement. So here this is the NAND gate, and the NOT gate is nothing but two inputs will be connected to one input, so that is A will become A bar NOT gate, and if you take one more NOR gate, A bar will become A, so that is a buffer, and XOR is nothing but A bar B plus A B bar. XNOR is nothing but A bar B bar plus A B. So in the same way here, if you take that here A, so this is A and this is B. So if you take A plus B whole bar, and here we are getting A bar B bar, and A bar B bar here, so this A bar and then B bar plus and then whole bar, it will become A dot B. So and here it will become A plus B whole bar, and if you do that operation here, Q equal to, so here A dot B plus A plus B whole bar and then complement, and by simplifying that you will get that A bar B plus A B bar. In the same way XNOR gate, so XNOR gate is also A B, so one NOR gate will give A plus B whole bar. So here we are taking A here and we are taking B here, so here this is A bar uh, like A plus B whole bar we have to take, and here also B like B plus A plus B whole bar we need to take, and by doing this one more OR gate, by simplifying this you'll get A bar B, by simplifying this you'll get A B bar, and again this NOR operation is nothing but A bar B plus A B bar whole bar, or else you can take that a complement is the XNOR gate. So all these are the logic gates, basic gates, universal gates, and then special gates. So logic gate, basic logic gates are the AND or NOT, and the NOT one more gate also we have discussed is the buffer. So buffer is very helpful wherever impedance matching is required, but the purpose is whatever input you give, same output you'll get that. And basic logic gates are AND or NOT. Then universal gates are NAND and NOR. So why we are calling NAND and NOR are universal gates is nothing but we can implement any logic gate using NAND and NOR that we discussed. And the special gates are there, XOR and XNOR. So this XOR and XNOR gate expressions, and then how to get that equation, Boolean expression also we have same. So we'll continue Boolean algebra in next coming lectures. Thank you.